We begin slowly, without urgency. In nature there are many kinds of boundaries. Some are easy to notice, like the edge of a shoreline where water meets land. Others are quieter, defined not by a visible line, but by a change in what is possible. Sound fades with distance. Light weakens as it travels. Even time behaves differently depending on where you are. Tonight's topic begins with one of these quiet boundaries, one that does not look like an edge, but still marks a limit. An event horizon is often spoken about as something dramatic, a point of no return, a place where reality breaks down. But in physics, it is something much calmer and more precise. It is simply a boundary defined by motion and light. Not a surface, not a wall, just a region where the rules we already know reach a natural conclusion. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. As always, you're welcome to share where you're listening from, a room, a train, a distant time zone. If this space helps you rest or think more gently, a like or subscription quietly supports the flow and keeps these long explorations possible. Now, let's begin and explore the science of what an event horizon actually is. To understand an event horizon, we don't need to start with black holes. We start with limits. In everyday life, limits are familiar. You can only hear a sound if it reaches you. You can only see an object if light from it arrives at your eyes. These are not philosophical limits, they are physical ones. They depend on speed, distance, and time. Light is central here. In our universe, light does not travel instantly. It moves at a fixed speed, the same everywhere. This speed is not just fast, it is a rule. Nothing that carries information can move faster. Because of this, there are always regions of space whose light has not reached us yet, and regions whose light never will. An event horizon is built from this simple idea. It is a boundary beyond which light cannot reach a particular observer, no matter how long they wait. Not because the light disappears, not because it is blocked, but because space and time themselves are arranged in a way that prevents escape. This boundary does not announce itself. There is no signpost, no sudden darkness. From far away, we can calculate where it is. We can describe it using equations, but locally it does nothing dramatic. It simply marks a change in what futures are possible. That is why physicists call it an event horizon. The word event here does not mean something explosive or sudden. It refers to events in space-time, moments that could happen, signals that could be sent. A horizon separates events that can affect an observer from events that cannot. Tonight, we will move slowly through this idea. We will see how gravity shapes space, how mass bends time, how light follows paths that are not always straight, and how, when these effects become strong enough, a horizon appears naturally, without intention, without violence, without mystery. There is nothing supernatural here, only consistency. The same physical laws applied patiently, even in extreme conditions. As you listen, there is no need to hold every detail. Understanding can be soft. Concepts can settle gradually, like dust in still air. We're not racing toward conclusions. We're simply tracing the edges of what can be known, and noticing how calmly the universe draws its boundaries. When physicists use the term event horizon, they are not naming an object. They are describing a condition. It helps to pause here, because much of the confusion around event horizons comes from imagining them as things you could touch or see. In reality, an event horizon is a boundary defined by motion, time, and the behavior of light. At its core, an event horizon is the edge of what can influence an observer. More precisely, it is the boundary beyond which events can no longer send signals to a particular location. If something happens beyond this boundary, No light from that event can ever arrive to tell you about it, not later. Not eventually, never. This is not because light is destroyed. Light still exists beyond the horizon. It still moves locally at the same speed it always does. The difference is that space and time are arranged in such a way that all possible paths for that light lead inward, not outward. From the perspective of an outside observer, escape is no longer part of the future. This idea may sound abstract, but it is grounded in very ordinary rules. Light travels at a finite speed, time moves forward, causes come before effects. An event horizon appears when these simple rules combine in an extreme but orderly way. It is helpful to notice what the definition does not include. An event horizon is not defined by pressure, temperature, or material density. It is not a region filled with matter. It does not radiate on its own. It does not pull things in like a vacuum cleaner. All of those are common images, but none of them are essential to the concept. Instead, the horizon is defined by geometry, by the structure of space-time itself. In everyday conditions, space is only slightly curved by gravity, and light can travel freely in many directions. But as gravity becomes stronger, those possible directions begin to narrow. Paths that once led outward now curve back inward. Eventually, there comes a point where outward paths no longer exist at all. That point is the event horizon. The word horizon is used deliberately. On Earth, a horizon marks the limit of what you can see, not because the world ends there, but because the surface curves away. The ocean continues beyond your view. The land does not stop. The horizon is about perspective, not termination. An event horizon works in a similar way, but with time included. It is not only a limit of sight, but a limit of influence. Beyond it, events still occur. Physics continues. But those events are no longer part of your causal future. Another important detail is that event horizons are observer-dependent. Whether a horizon exists depends on where you are and how you move. For someone falling inward, the horizon does not feel special or marked. For someone far away, it represents a clear boundary in calculations and predictions. This is why event horizons are often misunderstood as dramatic thresholds. In truth, they are quiet outcomes of well-tested laws. No new physics is required for their basic definition. They arise naturally from the combination of gravity, light, and time behaving exactly as they always do. As we move forward, we will see how this abstract definition becomes concrete in the context of black holes. But it is worth holding on to this calm foundation. An event horizon is not a place where reality breaks. It is a place where the future narrows, and the universe does this narrowing with remarkable consistency. To understand why event horizons exist at all, we need to spend some quiet time with light, not as brightness or colour, but as a carrier of information. In physics, light is how the universe tells us what is happening. Every image, every measurement, every observation depends on light, or something that behaves like it. When an object changes, when it moves, heats up, cools down, or emits energy, that change can only be known elsewhere if a signal travels outward. Light is the fastest such signal. Nothing can outrun it. This single fact shapes nearly every boundary we talk about in space and time. In everyday life, the speed of light feels infinite. When you turn on a lamp, the room fills with light instantly, at least to human senses. But on cosmic scales, light is slow enough that distance becomes delay. Looking across space is also looking back in time. The sunlight reaching your skin left the sun about 8 minutes earlier. The light from distant stars may have begun its journey before Earth existed. Because light takes time to travel, there are always limits to what can be known at any given moment. Some regions of the universe are simply too far away for their light to have reached us yet. Others are moving away so quickly due to cosmic expansion that their light never will. These are not dramatic limits. They are quiet consequences of speed and distance. Event horizons take this idea and apply it locally, around very strong gravity. Instead of distance being the main obstacle, space-time itself becomes the barrier. Light still moves at its usual speed, but the paths available to it are reshaped. Under normal conditions, light spreads outward in all directions. From a flashlight, photons travel forward, sideways, upward and downward, each following straight paths through space. Gravity slightly curves those paths, but the effect is small. Light can still escape. As gravity strengthens, those straight paths become curved more noticeably. Light passing near a massive object bends inward, following the curvature of space-time. This bending has been measured and confirmed many times, even around ordinary stars. Near a black hole, this curvature becomes extreme. The possible paths light can take begin to tilt inward. At a certain distance, even light emitted straight outward finds its path curving back. There is no longer a direction that leads away. The future of that light points inward no matter how it starts. That distance is the event horizon. This is why light is so central to the definition. The horizon is not about objects being crushed or destroyed. It is about signals failing to escape. If light cannot get out, then neither can any information. And if no information can escape, then nothing beyond the horizon can influence the outside world. It is also important to notice that light itself does not feel anything. It does not slow down locally. It does not struggle. From its own perspective, it always moves at the same speed. The restriction comes from the shape of space-time, not from resistance. This is a recurring theme in modern physics. Limits arise not because something is blocked, but because the geometry of the universe allows only certain paths. An event horizon is one of the clearest examples of this idea. As you rest with this concept, there is no need to picture dramatic scenes. Think instead of light tracing path through curved space, quietly following the only futures available to it. The horizon is simply where those futures stop leading outward. The speed of light is not just a measurement. In physics, it functions more like a rule that everything else must follow. It sets the maximum speed at which causes can lead to effects. It determines how space and time fit together. And it quietly decides where horizons can exist. It helps to release the idea that the speed of light is about light alone. Light simply happens to travel at this speed, but so does every signal that carries information. Gravity, electromagnetic changes, and even the structure of space-time itself all respect this limit. Nothing meaningful can travel faster. This rule is woven deeply into the universe. It does not depend on where you are or how you move. Whether you're standing still, orbiting a planet, or drifting through intergalactic space, the speed of light remains the same. This consistency is one of the most tested facts in science. Because this speed is finite, time and space become linked. Distance is no longer just a measure of separation. It also becomes a measure of delay. The farther away something is, the longer it takes for its influence to reach you. This is why astronomers speak carefully when they say they are seeing something far away. They're always seeing the past state of that object. Under ordinary conditions, this delay is manageable. Space is arranged so that light can travel outward, even if it takes a long time. But the speed limit remains absolute. If space-time itself begins to move or curve in a way that outpaces light's ability to escape, a horizon forms. This may sound strange at first, space-time moving faster than light, but it is not space-time as a thing racing through space. It is the structure of space and time changing how paths connect. In strong gravity, the future direction of time tilts inward. What it means to move forward begins to align with moving deeper into the gravitational field. An event horizon appears when this tilt becomes complete, when all future directed paths, even those taken by light, lead inward. At that point, no signal can move outward fast enough, because outward is no longer part of the future. This is why no amount of energy or effort can overcome an event horizon. It is not a contest of speed. Even travelling at the speed of light is not enough, because the geometry itself has changed. The rule is not being broken, it is being fulfilled. The speed of light also explains why event horizons are so sharply defined. There is a precise boundary where escape becomes impossible. Just outside it, light can still make it out, though increasingly delayed and distorted. Just inside it, escape is no longer part of what can happen. This boundary does not shimmer or glow. It does not announce itself. It exists quietly, as a mathematical surface in space-time. Its calmness is part of its nature. The universe does not dramatize its rules. It applies them evenly. As you settle into this idea, notice how little force or struggle is involved. Horizons form not because something fails, but because everything works exactly as it should. The speed of light holds, time moves forward, space curves, and a boundary appears. When people first learn about gravity, it is often described as a force that pulls objects together. This description works well enough for everyday life. It explains why things fall, why planets orbit, and why you stay on the ground. But to understand event horizons, we need a quieter and more precise view. In modern physics, gravity is not treated as pulling force. It is understood as the curvature of space-time itself. Mass and energy change the shape of space and time, and objects move along the paths that shape allows. Nothing is being pulled in the usual sense. Everything is following the natural geometry. This idea can feel unfamiliar, but it is deeply practical. Imagine walking across flat ground. The shortest path between 2 points is a straight line. Now imagine walking across a curved hill. The shortest path may bend, even if you never choose to turn. The shape of the ground guides your motion. Space-time works in a similar way. In regions with little mass, space-time is nearly flat. Objects move in straight lines through time, and light travels outward easily. Near massive objects, space-time curves. The straightest possible paths become bent. This bending applies to everything: planets, falling objects, and even light. Light does not have mass, but it still follows space-time's geometry. When space-time curves, light curves with it. This view helps explain why gravity affects time as well as space. Near a massive object, time passes more slowly compared to far away. This is not a psychological effect. It has been measured with precise clocks. Gravity changes the rate at which time flows. As mass increases or becomes more concentrated, space-time curves more sharply. The paths that objects can follow become steeper and more inward. Under extreme conditions, this curvature becomes so strong that even the straightest possible paths for light lead inward. At that point, an event horizon appears. What matters here is that nothing special needs to happen at the horizon itself. There is no sudden increase in force, no sudden crushing. The curvature has been increasing smoothly all along. The horizon is simply the location where the geometry crosses a threshold. This also explains why an object falling toward a black hole does not feel a sudden change upon crossing the horizon. Locally, space-time still feels smooth. The curvature is strong but not infinite. There is no physical marker to signal the boundary. From far away, however, the horizon plays an important role in calculations. It defines which events can influence the outside universe. It separates futures that connect outward from those that do not. Seeing gravity as geometry allows us to let go of dramatic images. Nothing is grabbing or dragging. Space and time are quietly shaped by mass, and motion follows. As you listen, you can allow this idea to settle without strain. Gravity does not need to feel intuitive to be gentle. It is simply the universe choosing the straightest possible paths, even when those paths curve deeply inward. Mass does not need to move or act to change the universe. Its presence alone is enough. Simply by existing, mass alters the structure of space-time around it. This change is not abrupt or localized to a surface. It spreads smoothly outward, growing weaker with distance. For small masses, like a person or a rock, this effect is extremely subtle. The curvature they create is so slight that it is almost impossible to measure directly. Space remains nearly flat. Time flows almost uniformly. Objects move as if gravity were just a gentle pull. As mass increases, the effect becomes more noticeable. A planet like Earth curves space-time enough to hold an atmosphere and keep the Moon in orbit. Time near Earth's surface runs slightly slower than time far away. These differences are tiny, but real, and modern technology accounts for them. A star curves space-time more strongly. Near its surface, paths of light bend measurably. Time slows more noticeably. The structure of space becomes more steeply shaped, though still smooth and continuous. What matters most for event horizons is not just mass, but how concentrated that mass is. Spread a given mass over a large volume, and the curvature remains moderate. Compress the same mass into a smaller region, and the curvature increases sharply. This is why black holes are possible at all. They are not defined by having an unusual amount of mass, but by having mass packed into an unusually small space. When the concentration becomes extreme, space-time curves so strongly that outward paths disappear. There is no single moment when this suddenly happens. As mass compresses, escape becomes harder. Light emitted outward takes longer to climb away. Its frequency shifts. Its paths bend more steeply. The future gradually narrows. Eventually, a boundary forms where escape is no longer part of what space-time allows. That boundary is the event horizon. Importantly, this boundary depends only on mass and concentration, not on the composition of the object. Whether the mass came from hydrogen, iron, or something more exotic does not matter. The horizon does not care about material details. It is a geometric outcome. This universality is part of what makes event horizons so calm from a scientific perspective. They are predictable. Given enough mass in a small enough region, a horizon must appear. There is no special tuning required. Outside the horizon, space-time continues to curve smoothly. Inside, it curves even more strongly. But at the horizon itself, nothing singular happens. It is simply the location where the shape crosses a critical threshold. As you rest with this idea, you might notice how gradual everything is. Mass builds curvature. Curvature shapes paths. Paths define futures. The horizon is not an abrupt event, but the quiet result of accumulation. So far, gravity has appeared as something that increases smoothly. More mass, stronger curvature, more concentration, steeper paths. There is nothing sudden or violent in this picture. But there is a point where the effects become unfamiliar, not because the rules change, but because their consequences grow large. Extreme gravity begins when space-time is curved so strongly that ordinary intuitions fail. Distances behave oddly. Time flows at very different rates depending on position. Paths that once felt straight now bend sharply inward. Yet even here, the underlying laws remain the same. One way to understand this is to think about escape. Near Earth, escape is easy. You can jump, throw a ball, or launch a spacecraft, and if you give it enough speed, it will move away. Near a star, escape requires more energy, but it is still possible. Light itself escapes freely. As gravity strengthens, the energy needed to escape increases. Light emitted upward from a massive object loses energy as it climbs out, stretching to longer wavelengths. This is called gravitational redshift, and it has been measured in many contexts. In extremely strong gravity, this redshift becomes more pronounced. Light loses more and more energy as it tries to escape. To a distant observer, it appears increasingly dim and slowed. There comes a point where the redshift becomes infinite. Light emitted from that location would be stretched beyond detectability. Its energy fades towards zero before it can reach the outside world. This point corresponds exactly to the event horizon. From the outside, this looks like time itself slowing down near the horizon. Signals take longer and longer to arrive. Processes appear frozen. But this is a matter of perspective, not a physical halt. Locally, time continues normally. An object falling inward experiences nothing special at the horizon. Its own clocks tick steadily. Its surroundings behave according to the same local laws. This difference between local experience and distant observation is one of the most important features of extreme gravity. Physics allows both descriptions to be correct because they refer to different frames of reference. Extreme gravity also stretches objects unevenly. The difference in gravitational strength between one end of an object and the other can become significant. This effect, called tidal force, grows stronger as curvature increases. However, at the event horizon of very large black holes, these tidal effects can be surprisingly mild. Nothing requires the horizon itself to be destructive. The danger lies deeper in, not at the boundary. As we move through this idea, it becomes clear that extreme gravity is not chaotic. It is structured, predictable, governed by geometry. The event horizon emerges as a calm dividing line, not between safety and destruction, but between regions of space-time that connect outward and those that do not. To understand why event horizons exist in our universe, it helps to follow the quiet life cycle of stars. Not in detail, and not with drama, but as a sequence of physical balances that eventually run out. A star is not defined by fire or explosion. It is defined by balance. Gravity pulls inward, trying to compress the star. At the same time, energy produced in the core pushes outward, created by nuclear reactions that convert mass into energy. For most of a star's life, these two effects hold each other in place. As long as the core produces enough energy, the star remains stable. Its size, brightness and temperature may change slowly, but gravity is kept in check. Space and time around the star are curved, but not extremely so. Light escapes easily. The future remains open in many directions. Eventually, however, the fuel runs low. Nuclear reactions slow. Outward pressure weakens. Gravity, which never stops, begins to dominate. What happens next depends mostly on the star's mass. Smaller stars collapse gently, settling into dense but stable objects. Larger stars experience more dramatic changes. Their cores compress further. Temperatures rise briefly. In some cases, outer layers are expelled in powerful explosions, while the core continues to collapse. If the remaining core is massive enough, there is nothing left to stop the compression. No known pressure can resist gravity at that scale. The core shrinks, becoming smaller and denser, curving space-time more and more sharply. It is during this continued collapse that an event horizon can form. Importantly, the horizon does not appear because of the explosion or the violence of the star's death. It appears because mass becomes concentrated within a certain radius. Once the curvature reaches the critical level, escape paths vanish. From the outside, this process looks gradual. Light from the collapsing object becomes increasingly redshifted. Signals slow. The formation of the horizon appears to stretch over an extremely long time. From the perspective of the collapsing matter itself, the process continues smoothly. The horizon forms without fanfare. No signal announces it. Locally, physics remains ordinary. This difference in perspective is essential. An event horizon is not tied to a moment in time that everyone agrees on. It is tied to the structure of space-time and to which events can communicate with which observers. What matters for us is that black holes and their event horizons are not exotic exceptions. They are natural outcomes of stellar evolution under the same physical laws that govern everything else. Stars live quietly, they age, they change, and sometimes their mass settles into a shape so compact that space-time itself draws a boundary. That boundary is not an ending, it is a continuation, shaped by gravity and time. The phrase black hole often brings images of destruction or emptiness, but in physics, a black hole is defined in a much simpler and calmer way. It is a region of space-time where an event horizon exists. That is all. Everything else is detail. A black hole is not a hole in space. It is not an empty region. It is not a tunnel or a drain. It is a configuration of mass and space-time that produces a boundary beyond which light cannot escape. From the outside, a black hole behaves like any other object with the same mass. Its gravity follows the same rules. Planets could orbit it. Stars could pass nearby. If the Sun were replaced by a black hole of the same mass, Earth's orbit would remain almost unchanged. This is an important point. Black holes do not actively pull things in more strongly than other objects of equal mass. Their uniqueness comes from what happens very close to them, where mass has been compressed into a very small region. The event horizon marks the size of the black hole, but not its contents. Inside the horizon, matter continues to fall inward. The internal structure is still an area of active research, but none of that uncertainty changes what the horizon represents. What makes a black hole black is not darkness inside it, but the absence of outgoing light. Light emitted from within the horizon cannot reach the outside. To distant observers, the region appears dark because no information escapes. It is also worth noting that black holes can grow. When matter falls in, the total mass increases. As mass increases, the event horizon expands. The boundary moves outward smoothly. There is no sudden jump. This growth is another reminder that the horizon is not a rigid surface. It is a geometric boundary that responds to changes in mass and energy. Black holes can also be quiet for long periods. If no matter falls in, they simply exist, curving space-time and maintaining their horizons. There is no ongoing activity required. When we speak about black holes in this series, we are not speaking about violent regions tearing the universe apart. We are speaking about stable solutions to Einstein's equations, predictable, consistent, and governed by clear rules. The event horizon is the defining feature. Everything else, jets, disks, radiation, happens outside it. Holding on to this calm definition helps remove fear from the concept. A black hole is not a cosmic monster. It is a region where the future is shaped in a particular way. An event horizon does not appear suddenly like a flash of light or a snapping line. It forms quietly, as a natural consequence of mass continuing to compress. There is no moment where space-time tears or breaks. The same rules apply before, during, and after its formation. As a collapsing object shrinks, the curvature of space-time around it grows stronger. Light emitted from its surface takes longer to escape. Signals become increasingly delayed. To a distant observer, this process appears to slow down. The closer the surface gets to the critical radius, the more extreme this delay becomes. Light takes longer and longer to climb away. Its energy decreases, its wavelength stretches. The object appears dimmer and redder. At the exact point where the surface crosses the critical radius, an event horizon forms. From that moment on, no light emitted from the surface can ever reach the outside universe. From far away, however, this moment is never seen directly. The final signals take infinitely long to arrive. The formation of the horizon appears to be spread out over an endless time. This is not a contradiction. It reflects the difference between coordinate time, measured by distant observers, and proper time, experienced locally. Locally, the horizon forms in a finite time. Distant observers describe it differently. This dual description is one of the reasons event horizons feel strange. But it is not a flaw in the theory. It is a feature of space-time when gravity becomes strong. The important point is that the horizon is not created by collapse violence. It is created by geometry. Once mass occupies a small enough region, the boundary must exist. After formation, The horizon remains stable as long as the mass remains. It does not oscillate or flicker. It simply sits as a quiet dividing line in space-time. This calm formation is often overlooked, but it reinforces a key theme. Event horizons are not dramatic events, they are quiet thresholds. Once an event horizon exists, the phrase "point of no return" is often used to describe it. This phrase can sound emotional or final, but in physics it has a very precise meaning. It is not about danger or destruction. It is about direction. Outside the event horizon there are many possible futures. An object can move inward, outward, or remain in orbit. Light can travel away or toward the massive object. The geometry of space-time allows multiple paths forward in time. At the event horizon this changes. The set of possible future paths narrows until only inward directions remain. This is not because something blocks the way out. It is because outward is no longer a future direction. To understand this, it helps to separate speed from direction. Even at the horizon, light still moves at its usual speed locally. Nothing slows it down. Nothing weakens it. But all future-directed paths point inward. It is similar to reaching a slope so steep that every step forward takes you downward, no matter which way you turn. You're still moving normally. The ground simply does not allow an upward path anymore. This is why no rocket, no matter how powerful, can escape once it is inside the horizon. It is not being overpowered, it is following space-time's geometry. Engines cannot change which directions exist in the future. From the outside, this restriction defines a clear boundary. From the inside, it does not feel like a barrier. Motion continues smoothly. Time continues to pass. This asymmetry, smooth experience locally, strict limitation globally, is central to understanding event horizons. They are not felt as walls. They are recognized as limits in prediction. The horizon also explains why nothing inside can influence the outside. Since no signals can escape, the interior is causally disconnected. Events inside the horizon cannot cause effects outside it. This is not about isolation in space. It is about separation in time. The futures simply do not intersect. As this idea settles, notice how little drama is required. Nothing is trapped by force. The universe simply arranges its futures in a particular way. It is very natural to imagine the event horizon as a surface, a shell around a black hole, sharp and physical, like the edge of a solid object. But this picture is misleading. An event horizon is not made of matter. It has no thickness, no texture, and no material strength. If you could approach an event horizon, there would be nothing to see or touch that marks it out. No line in space, no glowing boundary, no sudden darkness. Locally, space-time remains smooth. This is because the horizon is defined globally, not locally. It depends on the entire future structure of space-time, not on anything happening at that specific point. Whether a horizon exists cannot be determined by local measurements alone. An observer falling freely toward a black hole would cross the horizon without noticing a sudden change. Their instruments would behave normally. Their body would experience no special force at that boundary. This is often surprising, but it is a direct consequence of how gravity works in general relativity. Locally, gravity can always be transformed away by free fall. The horizon does not introduce a new force. From far away, however, the horizon plays a critical role. It separates regions of space-time into those that can communicate outward and those that cannot. It is a boundary in causal structure, not in substance. This distinction matters deeply. It means the horizon does not stop things. It does not reflect or absorb in the usual sense. Things cross it freely in one direction. They simply cannot return. The absence of a physical wall also explains why horizons can change. If mass increases, the horizon expands outward. If mass decreases, it shrinks. There is no rigid structure to break or bend. Thinking of the horizon as a geometric boundary rather than an object helps keep the concept calm and grounded. It is not something added to the universe. It is something the universe already contains when conditions allow. As you rest with this idea, you may notice how quiet it feels. A boundary with no surface, a limit with no barrier, just a change in what futures are possible. From far away, the behaviour of objects near an event horizon looks very different from what those objects experience themselves. This difference is not an illusion or a mistake. It comes from how time and light behave in strong gravity. Imagine watching an object fall toward a black hole from a great distance. At first, its motion looks ordinary. It accelerates inward, moving faster as it approaches. Light from the object still reaches you easily, carrying information about its position and motion. As the object gets closer to the event horizon, something subtle begins to change. The light it emits takes longer to escape. Each signal must climb out of deeper curvature. As it does, the light loses energy. Its wavelength stretches toward the red end of the spectrum. To the distant observer, the object appears to slow down. This is not because it is actually slowing in its own frame, but because each successive signal takes longer to arrive. The time between signals grows. Motion appears stretched out. Closer and closer to the horizon, this effect becomes more extreme. The light becomes dimmer and redder. The object seems to approach the horizon more and more slowly, never quite crossing it. In fact, according to the distant observer's clock, the crossing takes an infinite amount of time. The final signals are delayed without limit. They fade away before arrival. This is why we never see anything cross an event horizon from the outside. Not because it does not cross, but because the information about that crossing never reaches us. This perspective is sometimes misunderstood as meaning the horizon never truly forms. But this is not correct. The horizon exists as a feature of space-time, even if its formation cannot be witnessed directly by a distant observer. This distinction is important. Physics allows different observers to describe the same process in different, equally valid ways. The outside description emphasizes delays and fading signals. The falling description emphasizes smooth passage. Neither is more real than the other. They are descriptions tied to different frames of reference. As you settle into this idea, notice how calmly the universe handles disagreement. There is no single privileged viewpoint. Each observer describes what light and time allow them to see. The event horizon remains quiet, unseen, and precise, defined not by appearance, but by connection. While a distant observer sees motion slow and fade near the event horizon, the experience of the object that is falling inward is very different. This difference is not a paradox. It is a natural result of how time and measurement work in curved space-time. For the falling object, time passes normally. Its internal clocks tick at their usual pace. Processes inside the object, chemical reactions, biological rhythms, electronic signals, continue without interruption. There is no moment when time hesitates or stretches from its own point of view. As the object approaches the event horizon, nothing dramatic announces the boundary. There is no sudden darkness, no flash, no physical barrier. The laws of physics in the immediate surroundings remain the same as they were moments before. This is because the event horizon is not defined by local conditions. It is defined by the global structure of space-time, by which future paths exist. Locally, space-time remains smooth at the horizon, especially for large black holes where tidal effects are small at that distance. If the black hole is very massive, the curvature at the horizon can be gentle enough that the falling object notices nothing unusual at all when crossing it. There is no sharp increase in force, no sudden compression, no clear signal that anything has changed. From the falling object's perspective, crossing the horizon happens in a finite amount of time. There is no sense of delay or freezing. The boundary is crossed quietly, without ceremony. This contrast between perspectives can feel unsettling at first. how can one observer say the crossing never happens while another experiences it normally? The answer lies in the role of light and communication. The distant observer relies on light signals to track the falling object. Those signals become increasingly delayed and redshifted. Eventually they stop arriving. The falling object, however, does not depend on sending signals outward to experience time. Its own future continues uninterrupted. This difference does not mean one observer is wrong. It means that time is not universal. Each observer carries their own clock shaped by their path through space-time. Understanding this helps dissolve some of the fear surrounding event horizons. There is no sudden moment where reality breaks or awareness ends at the boundary. The horizon is not a cliff, it is a line in the map of futures. As you listen, you can let this idea rest gently. Physics does not require drama. Even at the edges of what can be known, it moves quietly, one moment following the next. Time is often treated as something steady and uniform, always moving forward at the same rate. In everyday life, this works well enough. Our clocks agree with one another, days pass predictably. But gravity quietly alters this picture, and near an event horizon, the effect becomes impossible to ignore. Time dilation is the term physicists use to describe how time can pass at different rates depending on conditions. One cause is motion, another is gravity. The stronger the gravitational field, the more slowly time passes compared to regions with weaker gravity. This slowing of time is not a visual trick or a mental illusion. It has been measured directly. Clocks placed closer to Earth's surface tick slightly more slowly than clocks in orbit. The difference is tiny but real, and modern navigation systems correct for it continuously. Near a black hole, gravity is far stronger. As an object approaches the event horizon, time for that object slows relative to a distant observer. Each second experienced locally corresponds to more and more time passing far away. From the distant point of view, this slowing becomes extreme. Signals from near the horizon arrive increasingly spaced out. Processes appear to stretch. Motion appears to fade into stillness. But again, this does not mean time stops for the falling object. Locally, time always feels normal. The slowing only appears when comparing clocks at different gravitational depths. This distinction is important. Time dilation is not something you feel directly. It is something you observe when comparing different paths through space-time. Each observer's time is valid along their own path. At the event horizon, time dilation relative to infinity becomes infinite. This is why distant observers never see the crossing completed. But locally, nothing infinite occurs. Understanding time this way helps keep the concept grounded. There is no frozen moment at the horizon. There is no pause in experience. There is only a growing difference between perspectives. As you rest with this idea, notice how gently physics treats time. It stretches and reshapes it, but never tears it. Even near the most extreme boundaries, time continues one quiet moment at a time. Light usually feels like the simplest thing in the universe. It moves in straight lines. It spreads outward. It connects distant places. But near a black hole, light still follows the same rules. It simply follows them through a much more curved space-time. In general relativity, light always travels along the straightest possible paths. These paths are called geodesics. In flat space, a geodesic looks like a straight line. In curved space-time, a geodesic can bend, loop, or even circle, not because light is forced to turn, but because straight itself has changed meaning. Far from the black hole, light behaves almost normally. It may bend slightly as it passes by, an effect known as gravitational lensing. This bending has been observed many times and matches theoretical predictions with high precision. As light moves closer, the curvature increases. Paths that once led outward now curve inward. Some light can enter looping orbits, circling the black hole before either escaping or falling in. These orbits are unstable. A small change sends the light one way or the other. Closer still, the outward pointing paths disappear entirely. At the event horizon, every future directed path for light points inward. Light emitted exactly at the horizon can hover there in a delicate balance, neither escaping nor moving outward, but this balance is fleeting. Any disturbance sends it inward. Inside the horizon, the idea of outward loses its usual meaning. All light paths lead deeper in. This is not because light slows or weakens, but because the geometry gives it no alternative. This behaviour of light explains many observed features of black holes. It explains why we see a dark shadow surrounded by bright rings. It explains why the horizon itself cannot be imaged directly. It explains why information stops flowing outward. What is striking is how consistent this all is. Light does exactly what it always does. It follows space-time. Space-time simply becomes very curved. As you let this idea settle, imagine light tracing these paths quietly, without effort or resistance. No struggle, no barrier, just motion shaped by geometry, right up to the edge where futures turn inward. When we speak about seeing a black hole, we need to be careful with language. A black hole itself does not emit light. The event horizon is not visible, yet we can still observe something real and measurable, the shadow a black hole casts against its surroundings. This shadow is not a silhouette of a solid object. It is a region where light paths are missing. Light that would have reached us is instead bent inward or captured. What remains is a dark shape outlined by glowing matter around it. Near many black holes, gas and dust collect into a rotating disk. This material heats up as it moves, emitting large amounts of light. The disk does not fall straight in. It orbits, gradually losing energy and spiraling inward. This glowing structure provides a bright background against which the black hole's effects become visible. As light from this disk travels toward us, some of it passes near the black hole. The strong curvature of space-time bends those light paths. Some light is redirected, some is delayed, some is captured entirely. The result is a dark central region, the shadow. The size of this shadow is larger than the event horizon itself. It includes not only the horizon, but also the region where light is forced into unstable orbits before falling inward. This makes the shadow a reliable indicator of the black hole's presence and mass. When astronomers captured the first images of black hole shadows, they were not photographing the horizon directly. They were observing the absence of light in a precise, predictable pattern. The shape and size matched theoretical expectations remarkably well. This is important. It shows that event horizons are not abstract ideas detached from observation. They leave signatures in the behaviour of light. Even though the horizon itself cannot be seen, its influence shapes what we observe. The shadow is steady. It does not flicker or move erratically. It reflects the stability of the underlying geometry. This steadiness is another reminder that black holes are not chaotic objects. They are governed by clean, consistent laws. As you rest with this image, a dark centre surrounded by light, notice how quiet it feels. Nothing is exploding. Nothing is tearing apart. Light is simply following paths, and where those paths end, darkness appears. One of the most subtle aspects of an event horizon is that it is not defined by what is happening right now. It is defined by what can happen later. This makes it different from most physical boundaries we're used to thinking about. A wall is defined by its material presence. A shoreline is defined by geography. But an event horizon is defined by the structure of the future. Specifically, it is the boundary separating events that can eventually send signals outward from those that cannot, no matter how much time passes. This means that, in a strict sense, you cannot determine whether a horizon exists at a particular location using only local measurements taken at that moment. You could measure gravity, curvature, and motion, and still not know for certain whether you are inside or outside an event horizon. The reason is that the horizon depends on the entire future evolution of space-time. It depends on whether light emitted from that point will ever reach a distant observer, even billions of years later. That question cannot be answered instantly or locally. This future-based definition can feel unsettling at first. We are used to thinking of physics as something determined here and now, but space-time is a four-dimensional structure, and some of its features only make sense when viewed as a whole. This does not make event horizons vague or subjective. Their existence can still be calculated precisely. Given the mass, energy, and geometry of space-time, physicists can determine where the horizon must be. But the definition itself reaches forward in time. This also explains why horizons can shift. If matter falls into a black hole, the horizon expands. If energy slowly escapes, the horizon can shrink. The boundary adjusts as the future possibilities change. In this way, an event horizon is less like a fence, and more like a contour on a map of time. It marks where futures diverge. On one side, influence can still spread outward. On the other, it cannot. As you listen, it may help to let go of the need to picture the horizon as a present moment. It is a relationship between now and later. A quiet agreement between geometry and time. The phrase, "no return," often carries emotional weight. It suggests finality, loss, or danger. In the context of event horizons, however, it has a very specific and limited meaning. It does not describe what happens to objects. It describes what happens to influence. Outside an event horizon, events can affect the rest of the universe. Light can escape. Signals can be sent. Causes can lead to distant effects. Inside the horizon, this is no longer true. Events continue to occur, but their consequences remain confined. This confinement is not enforced by force or obstruction. It arises from the structure of space-time. The paths that would carry influence outward simply do not exist in the future. Because of this, no return does not mean instant destruction or disappearance. An object inside the horizon still exists. It still has structure. Processes continue according to local physics. What changes is connection. The interior becomes causally separate from the exterior. The two regions no longer share futures. This distinction is important for keeping the idea grounded. The horizon is not a one-way door that slams shut. It is a boundary that organizes what can interact with what. In many ways, this idea appears elsewhere in physics. Sound cannot travel in a vacuum. Heat does not flow from cold to hot without work. These are not violent restrictions. They are limits defined by underlying laws. The event horizon is similar, but deeper. It limits the flow of information itself. As you rest with this concept, notice how quietly it operates. There is no signal of separation, no announcement. The universe simply arranges its causal structure and continues. When physicists talk about information, they are not thinking about messages or data in the everyday sense. In physics, information means something more basic. It refers to the complete description of a physical system, the positions of particles, their energies, their relationships. Information is what allows the universe to evolve in a consistent way. Event horizons bring this idea into focus because they mark a boundary for information flow. Once information crosses an event horizon, it can no longer influence the outside universe. Signals cannot escape. Causes inside cannot produce effects outside. This raises a quiet but important question. What happens to that information? From a classical point of view, the answer is simple. The information is still there, inside the horizon. It continues to exist and evolve. The outside universe simply cannot access it. Nothing mysterious is required. But when quantum physics enters the picture, the situation becomes more subtle. Quantum theory places strong rules on how information can behave. In particular, it suggests that information is never truly destroyed. This leads to a tension. If a black hole eventually disappears, as we will discuss later, and information cannot escape while it exists, Where does that information go? This question is known as the black hole information problem. It is not about danger or paradox in the everyday sense. It is about reconciling two very successful theories that describe nature at different scales. What matters for our understanding of event horizons is that the horizon itself plays a central role. It is the boundary where information flow changes character. Outside, information spreads and influences. Inside, it becomes hidden from the rest of the universe. Many modern ideas suggest that information may be encoded at or near the horizon itself, in subtle ways that do not violate known laws. These ideas are still being explored, refined, and tested. What is important here is not the unresolved details, but the tone of the question. Physics treats this as a calm problem, not a crisis. The horizon does not threaten the consistency of nature. It invites deeper understanding. As you listen, there is no need to follow every implication. It is enough to notice that event horizons are not just limits on motion. They are limits on knowledge, quiet, precise, and deeply connected to how the universe stores its history. So far, an event horizon has sounded absolute. Once information crosses it, there is no influence outward. The boundary feels permanent. But when quantum physics is added carefully to the picture, something subtle changes. Not violently, not suddenly, but slowly, over immense spans of time. In the 1970s, physicist Stephen Hawking showed that black holes are not perfectly black. They can emit a very small amount of energy. This process is now called Hawking radiation. The idea does not involve light escaping directly from inside the horizon. That would still be impossible. Instead, it arises from quantum effects near the horizon itself. In quantum physics, empty space is not truly empty. Even in complete darkness, there are tiny fluctuations. Pairs of particles briefly appear and disappear. Most of the time, these pairs cancel out almost immediately, leaving no lasting effect. Near an event horizon, however, the situation is slightly different. The strong curvature of space-time can separate these pairs. One particle may fall inward, while the other escapes outward. To a distant observer, it appears as though the black hole has emitted energy. This emission is extremely weak. For stellar or supermassive black holes, Hawking radiation is far smaller than any other effect. The black hole absorbs far more energy from its surroundings than it emits. For all practical purposes, it remains dark and stable. But over extraordinarily long timescales, far longer than the current age of the universe, this radiation becomes important. If a black hole were completely isolated, it would very slowly lose mass. As its mass decreases, the event horizon would shrink. This does not contradict the idea of the horizon as a boundary. The horizon still functions as a limit on information flow at any given moment. Hawking radiation does not carry detailed information from inside. It changes the horizon's size gradually, not its nature. What matters here is the tone of the process. Nothing dramatic happens. There is no explosion, no sudden release, just a quiet, steady leaking of energy, governed by the same laws everywhere else. Hawking radiation reminds us that event horizons are not eternal features carved into the universe. They exist as long as conditions support them. When those conditions change, even very slowly, the horizon responds. As you rest with this idea, notice how patient the universe is. Even its most extreme objects change gently, over timescales so long that urgency disappears. When a black hole loses mass, its event horizon responds immediately and precisely. There is no delay, no hesitation. The size of the horizon depends directly on the amount of mass present. Less mass means less curvature, and less curvature means a smaller region where escape is impossible. Hawking radiation provides a mechanism for this mass loss, but it operates extraordinarily slowly. For black holes formed from stars, the timescale for significant shrinking is vastly longer than the age of the universe. For supermassive black holes, it is longer still. This immense timescale is important. It means that, for almost all practical purposes, black hole horizons are stable. They do not flicker or fluctuate noticeably. They change so gradually that the universe around them evolves many times over before the change becomes relevant. As the horizon shrinks, the boundary of no escape moves inward. Regions that were once inside the horizon become outside. The causal structure of space-time adjusts smoothly. This process raises deep questions about information, but it does not undermine the basic definition of the horizon. At every moment, the horizon marks the boundary between futures that connect outward and those that do not. The idea of a shrinking horizon also reminds us that event horizons are not rigid or permanent objects. They are dynamic features of space-time, responding to the distribution of mass and energy. There is something calming about this. Even the most extreme boundaries are not frozen. They participate in the slow flow of the universe. As you settle into this idea, you can let go of the image of black holes as eternal traps. They are part of a changing cosmos, shaped by time as much as by gravity. Black holes come in many sizes, but the rules that govern their event horizons are remarkably simple and consistent. Whether a black hole is formed from a single collapsing star or sits at the centre of a galaxy, with the mass of millions of suns, the same principles apply. The size of an event horizon depends only on mass. More mass means a larger horizon. Less mass means a smaller one. The composition of the matter, its temperature, its history. None of these details matter once the horizon is defined. Space-time responds only to the total mass and energy present. A stellar mass black hole may have an event horizon only a few tens of kilometers across. A supermassive black hole can have a horizon larger than the orbit of planets. Yet if you were to hover just outside either horizon, the defining feature would be the same, the boundary beyond which light cannot escape. What changes with size is how extreme the local environment feels. Near a small black hole, the curvature of space-time changes very rapidly over short distances. Tidal forces are strong. Differences in gravity from one point to another are intense. Near a very large black hole, those gradients are gentler at the horizon. Space-time curves deeply, but smoothly. An observer crossing the horizon of a supermassive black hole might experience nothing unusual for some time afterward. Despite these differences, the horizon itself behaves in the same way. It marks the same causal boundary. It obeys the same geometric rules. It responds to mass in the same proportional way. This universality is one of the quiet strengths of physics. The universe does not invent new rules for larger scales. It applies the same ones patiently, whether the system is small or vast. As you rest with this idea, notice how comforting the consistency can be. No matter how large or small the black hole, the event horizon remains a calm, predictable boundary. Drawn by gravity, shaped by time, and governed by the same steady laws everywhere. Although event horizons are most often associated with black holes, the idea itself is more general. A horizon appears whenever there is a limit on how far signals can travel, given the structure of space, time, and motion. Black holes are simply the most extreme and familiar example. One such context is accelerated motion. An observer who accelerates continuously can develop a horizon of their own. There may be regions of space from which light can never reach them, not because of gravity, but because their motion carries them away too quickly. This is sometimes called an acceleration horizon. Another example appears in cosmology. Because the universe is expanding, there are distant regions whose light will never reach us, even given infinite time. The expansion stretches space so rapidly that signals from those regions can never overcome the increasing separation. These horizons are not identical to black hole event horizons, but they share an important feature. Each marks a boundary in what can be observed or influenced. Each separates events that can be part of an observer's future from those that cannot. This broader view helps place black hole horizons into context. They are not isolated oddities. They are part of a family of boundaries that arise naturally whenever space and time impose limits on communication. Seeing this pattern reduces mystery. The universe contains horizons because it contains rules about speed, causality, and geometry. Whenever those rules combine in certain ways, a horizon appears. As you rest with this idea, you may notice how ordinary it feels. Even in daily life, there are limits to what we can hear or see. Cosmic horizons extend this idea, calmly and consistently to the larger scales. Beyond black holes and acceleration, there is another kind of horizon that shapes our understanding of reality. The horizon of the observable universe itself. This horizon is not centered on any object. It is centered on us, or more precisely, on any observer, wherever they happen to be. Because the universe has a finite age, and because light travels at a finite speed, there is a limit to how far we can see. Light from very distant regions has simply not had enough time to reach us yet. Those regions may exist, but they are not part of our observable universe. In addition to this time limit, cosmic expansion introduces another boundary. Space itself is stretching. Distant galaxies are moving away from us not because they are travelling through space, but because space between us and them is growing. Beyond a certain distance, this expansion happens so quickly that light emitted today will never reach us, no matter how long we wait. This creates what is sometimes called a cosmic event horizon. It is not caused by gravity pulling inward, as with black holes, but by expansion carrying regions away. Still, the result is similar, a boundary in what futures can connect. Events beyond this horizon cannot influence us. Their light will never arrive, their changes will never be observed, yet they are not destroyed or erased. They simply lie outside our causal reach. This cosmic horizon is not a sharp line you could point to in space. Like all horizons, it depends on time and motion. As the universe evolves, the horizon changes. New regions enter view. Others drift beyond reach. What is striking is how familiar this idea has become. Astronomers work with these limits every day. They map what can be seen, infer what lies beyond, and accept that some regions will remain forever unobservable. Placing black hole event horizons alongside cosmic horizons helps ground them. Both arise from the same quiet facts. Light takes time, space evolves, and not everything can connect with everything else. As you rest with this idea, notice how natural it feels. The universe does not promise total access. It offers a region of connection, bounded gently by time and motion. When we step back from the mathematics and definitions, event horizons reveal something very simple. They mark limits, not limits of existence, but limits of access. They tell us where knowledge can travel and where it cannot. Outside a horizon, information moves. Light carries details, changes propagate, causes lead to effects that can be measured elsewhere. Inside a horizon, this chain quietly ends. Events still occur, but their outcomes remain local. This distinction is important because it keeps event horizons grounded in observation rather than imagination. A horizon does not say that something stops existing. It says that something stops being knowable to a given observer. Physics is comfortable with this idea. Many theories already include limits of knowledge. We cannot measure both the position and momentum of a particle with perfect precision. We cannot observe a system without interacting with it. Horizons extend this pattern to space-time itself. What makes event horizon special is that the limit is absolute. No improvement in technology, no increase in patience, no clever detour can overcome it. The boundary is not practical, it is fundamental. At the same time, this limit is clean and precise. It is not fuzzy or uncertain. Given a space-time and an observer, the horizon can be calculated exactly. The universe is very clear about where access ends. This clarity is calming. There is no trick being played. The horizon is not hiding something arbitrarily. It follows directly from rules that apply everywhere else as well. Seeing horizons this way helps remove emotional weight from the concept. They are not warnings or threats. They are features of a universe that values consistency over completeness. As you listen, you can let this idea settle gently. Understanding does not require total reach. It requires knowing where reach ends, and accepting that boundary without tension. One of the recurring themes in our exploration of the event horizons is the difference between what is measured and what is experienced. These two perspectives are both valid, but they answer different questions. Measurement relies on signals. It depends on light arriving at instruments, clocks being compared, data being transmitted. Whenever signals are delayed, redshifted, or blocked, measurement changes. Experience, on the other hand, is local. It depends on what happens along a single path through space-time. It does not require communication with distant observers. It unfolds moment by moment. Near an event horizon, these two perspectives diverge sharply. A distant observer measures signals that slow, fade, and never quite complete the story. A falling observer experiences smooth, continuous time. This difference does not mean that reality splits or becomes inconsistent. It means that space-time allows multiple, equally valid descriptions, each tied to a specific frame of reference. Physics has learned to work carefully with this idea. Rather than asking which description is true, it asks what each description can predict. As long as predictions match observations within their respective frames, the theory holds. This approach removes drama from disagreement. Event horizons do not create contradictions. They reveal how deeply observation depends on position and motion. As you rest with this idea, you may notice how gently it reframes understanding. You do not need a single absolute viewpoint. You need clarity about perspective. When event horizons are first encountered, they are often framed as terrifying or catastrophic. They are described as points of no return, places where time stops or edges of reality. But when we step through the physics carefully, a different picture emerges, one that is remarkably calm. An event horizon is not a place where laws break down. It is a place where the laws we already know reach a natural conclusion. Nothing new or exotic is required to define it. Gravity curves space-time. Light follows space-time. Time moves forward. From these ingredients alone, a horizon appears. There is no instability at the horizon, no turbulence, no eruption of energy. The geometry is smooth. The equations behave well. From the standpoint of physics, the horizon is one of the most orderly features in the universe. This orderliness is why event horizons are predictable. Given enough mass in a small enough region, the boundary must exist. Given less mass, it must not. There is no ambiguity. The universe does not hesitate. It is also why horizons persist. They do not need to be maintained. They do not require constant activity. They simply remain as long as the conditions support them. When seen this way, event horizons lose their emotional charge. They become quiet markers of structure, like coastlines drawn by gravity and time. As you settle with this idea, notice how much tension drains away. The universe does not rush or panic at its edges. It holds them steadily, allowing everything else to flow. Event horizons cannot be touched, crossed, and reported back from, or observed directly in the way we observe stars or planets. And yet scientists study them with confidence and precision. This may seem surprising at first, but it follows a familiar pattern in science, understanding things by their effects. Much of science works this way. We cannot see atoms directly with our eyes, but we infer their existence from consistent patterns in experiments. We cannot watch gravity itself, but we measure how objects move. In the same way, we do not observe event horizons directly. We observe how matter, light, and time behave near where a horizon must be. Mathematics plays a central role here. The equations of general relativity describe how mass and energy shape space-time. When these equations are applied to extremely dense objects, they consistently predict the formation of horizons. These predictions are not vague. They specify precise sizes, shapes, and behaviors. Once a prediction is made, scientists look for indirect confirmation. They observe how stars orbit unseen companions. They track how gas accelerates and heats as it spirals inward. They measure how light bends and how time appears to slow in strong gravitational fields. When these observations match predictions, confidence grows. Not emotional confidence, but structural confidence. The sense that many independent pieces fit together without strain. Computer simulations also play a role. By modelling the equations in detail, scientists can see how horizons form, how they respond to incoming matter, and how they remain stable. These simulations do not invent behaviour, they reveal what the equations already contain. Importantly, scientists remain careful about language. They do not claim to see the horizon itself. They say the data is consistent with its existence. This restraint keeps the science calm and grounded. As you rest with this idea, notice how patient the process is. No leaps of faith, no need for spectacle, just careful reasoning, repeated checks, and a quiet trust in patterns that hold. Although event horizons themselves cannot be seen, images still play an important role in understanding them. These images are not direct photographs of a boundary. They are visual summaries of how light behaves in a curved space-time, shaped by careful observation and theory working together. When astronomers create images of black holes, they are not capturing a surface. They are mapping the paths of light around a region where escape becomes impossible. Bright rings, distorted shapes, and dark centers all arise from predictable light trajectories near a horizon. These images matter because they connect abstract ideas to measurable reality. They allow us to test whether space-time behaves the way our equations say it should. When the observed light patterns match predictions, confidence in the underlying concepts grows. What is especially calming about these images is how steady they are. They do not reveal chaos, they reveal structure. The dark region remains stable. The surrounding light follows smooth, repeatable paths. Nothing flickers unpredictably. Images also help clarify scale. They remind us that event horizons are not mystical points. They have size. That size depends on mass, and it can be measured indirectly through light. At the same time, these images teach humility. They show us the limits of what can be visualized. No amount of resolution will reveal the horizon itself. The boundary remains defined by absence, not presence. As you rest with this idea, notice how images serve as bridges, not to spectacle, but to understanding. They allow us to see the consequences of invisible structure and to trust that unseen boundaries can still be real. By this point, the event horizon no longer needs to feel like a special exception in the universe. It begins to look more like a pattern, something that appears whenever certain conditions quietly line up. Across nature, boundaries often emerge without intention. Shorelines form where land meets water. Ice forms at a specific temperature. Sound fades beyond a certain distance. None of these boundaries are imposed from outside. They arise naturally from underlying rules. Event horizons belong to this same family. They appear when limits on speed, gravity, and time intersect. Light can only move so fast. Space-time can only curve so much before futures rearrange. When those facts combine, a horizon forms. What is striking is how little choice is involved. The universe does not decide to create a horizon. It simply follows its rules, and the boundary appears as a consequence. This pattern shows up again and again. in black holes, in accelerating frames, in the expanding universe. Different causes, same result, a limit on connection. Seeing horizons as patterns rather than anomalies helps soften the concept. They are not warnings, they are not failures, they are markers of structure, signs that the universe is consistent enough to produce predictable edges. As you rest with this idea, notice how familiar it feels. Nature often reveals itself not through dramatic events, but through repeated, reliable outcomes. The event horizon is one of those outcomes. Quiet, orderly, expected. Event horizons exist on scales that are far beyond everyday experience. They involve distances measured in kilometres or millions of kilometres, time stretching over years or billions of years, and masses far greater than anything we encounter directly. It is natural that they feel abstract. But the physics that creates an event horizon is not distant from us. It grows out of the same rules that govern falling objects, orbiting satellites, and the passage of time on Earth. The difference is not in kind, but in degree. Human intuition is tuned to a narrow range of scales. We are comfortable with speeds far below that of light. We are familiar with gravity that is strong enough to hold us down, but not strong enough to distort time noticeably. When we move beyond these ranges, intuition fades, but the rules do not change. Event horizons remind us of this gently. They show what happens when familiar laws are allowed to operate without the constraints of everyday scale. Gravity curves space-time a little around Earth. Around a black hole, it curves space-time a lot. Light still follows the same rule. Time still moves forward. From a human perspective, this can feel humbling. There are regions of the universe where our direct understanding cannot reach, but there is also something reassuring in knowing that the same structure holds everywhere. As you settle into this thought, you may notice how smallness and belonging can coexist. We are limited in scale, but not excluded from understanding. Even boundaries that dwarf us can be approached calmly, through patience and clarity. Event horizons can feel paradoxical because they seem both static and dynamic at the same time. They appear as fixed boundaries, yet they exist within a universe that is always changing. Understanding this balance helps the idea settle more gently. At any given moment, an event horizon marks a precise location in space-time. It defines which futures can connect outward and which cannot. In that sense, it is steady. It does not flicker or wander without cause. At the same time, the universe around it continues to evolve. Matter falls in. Energy radiates away. Space expands. Over long periods, these changes can shift the horizon's position. It may grow as mass accumulates, or shrink as mass slowly disperses. This combination of stillness and change is common in nature. A riverbank may hold its shape for years while water flows past it. A coastline may appear stable while tides rise and fall. The boundary persists even as the system moves. Event horizons follow this pattern. They are stable features of space-time at a given moment, yet they are not frozen forever. They respond to the slow rhythm of cosmic change. This helps remove another common misconception, that horizons represent absolute endings. They do not halt the universe, they participate in its long evolution. As you rest with this idea, you may notice how comforting it is. Even the strongest boundaries are part of motion. Nothing is locked in place. Everything flows within structure. When we look far ahead in time, far beyond human history, beyond the lifespan of stars and galaxies, black holes and their event horizons still follow the same calm rules. Nothing dramatic is scheduled. There is no final act, only gradual change. In the distant future of the universe, stars will finish burning their fuel. Galaxies will grow quieter. New black holes will stop forming. What remains will be a sparse cosmos. Long-lived objects drifting through expanding space. Black holes will be among the most persistent structures in that future. For immense spans of time, they will simply exist, curving space-time and maintaining their horizons. Nothing about this state is unstable. A black hole does not decay quickly. It waits, very slowly, unimaginably slowly. Hawking radiation will continue to carry energy away. As this happens, the mass of the black hole will decrease. The event horizon will shrink in response, always maintaining the same relationship between mass and boundary. For stellar mass black holes, this process takes far longer than the current age of the universe multiplied many times over. For supermassive black holes, the timescale is so long that ordinary language loses meaning. But even then, the process is smooth and orderly. Eventually, if nothing falls in to replace the lost mass, a black hole could disappear entirely. The horizon would shrink to nothing. The boundary would simply cease to exist. This is not an explosion, not a collapse, just a quiet fading, consistent with the same rules that created the horizon in the first place. What matters here is the tone of the future. Event horizons are not permanent scars in the universe. They are temporary features, present when conditions allow, gone when they do not. As you listen, you can let this long view soften your sense of urgency. Even the most extreme boundaries are patient. They arrive without noise, remain without effort, and leave without drama. By now, event horizons can be seen not as isolated features, but as part of a broader structure. The universe is filled with limits, not arbitrary ones, but limits that arise naturally from how space, time, and matter behave together. There are limits to speed, limits to measurement, limits to how much energy can be concentrated in one place without changing the geometry around it. Event horizons are one expression of this deeper pattern. These limits do not feel restrictive from the universe's point of view. They feel stabilizing. They prevent contradictions. They ensure that causes led to effects in a consistent order. They allow the universe to evolve without tearing itself apart. An event horizon is one of the clearest examples of this stabilizing role. It prevents information from propagating in ways that would violate the structure of space-time. It preserves the integrity of causality. Seen this way, horizons are not failures of access. They are successes of order. They mark where the universe draws a clear, clean boundary and maintains it. As you rest with this idea, you may notice how peaceful it feels. The universe does not try to be infinite in every direction at once. It allows connection where it can, and separation where it must. By this point, event horizons no longer need to feel threatening or dramatic. They can be understood as expressions of a universe that is precise about what is possible, and equally precise about what is not. In everyday life, boundaries often carry emotional weight. They can feel like losses or restrictions. In physics, boundaries are different. They are descriptions, not judgments. They say nothing about value or meaning. They simply describe how systems behave. An event horizon does not forbid curiosity. It does not punish exploration. It does not erase what lies beyond it. It calmly states a fact. Information from this region cannot reach that one. Accepting this kind of boundary does not weaken understanding. It strengthens it. Once we know where influence ends, we can reason clearly within the region where connection still exists. Science advances not by denying limits, but by working carefully within them. There is something steadying about this. The universe does not promise complete access, but it offers consistency in exchange. The same rules apply everywhere. When they lead to a boundary, that boundary holds. This acceptance is not passive. It is active clarity. It allows us to stop straining against what cannot be changed and to focus on what can be known well. As you rest with this idea, you may notice how naturally the mind begins to settle. Boundaries, when understood, remove uncertainty. They replace tension with structure. At the beginning of this journey, we spoke quietly about boundaries, the kind that do not look like edges but still shape what is possible. As we return to that idea now, the event horizon can be seen clearly as one of those boundaries. It is not a dramatic line drawn across space. It is not a warning sign. It is a natural outcome of familiar rules applied patiently. Light moves at a finite speed. Gravity curves space and time. Futures are shaped by geometry. From these simple facts, a horizon appears. Nothing about this requires fear. The horizon does not rush toward anything. It does not hunt or consume. It simply exists where escape paths end. It is as calm as a shoreline shaped by gravity and motion over long time. When we understand it this way, the event horizon becomes less of a mystery and more of a quiet fact, a reminder that the universe has structure and that structure includes limits. As you listen now, you may notice how the idea feels lighter than it did at first. The unknown has been replaced with clarity, the dramatic with the precise, the frightening with the understandable. This return is not about closing a loop or resolving a puzzle. It is about settling into familiarity. The boundary we began with is the same boundary we end with, now simply more clearly seen. What we have learned about event horizons is not a list of surprising facts, but a way of seeing. An event horizon is not an object, not a surface, not a dramatic edge. It is a boundary defined by light, time, and geometry. It exists because the universe has a speed limit, because gravity shapes space-time, because futures are not all equally reachable from every place. When these elements come together under extreme conditions, a horizon appears, quietly and inevitably. Nothing special needs to happen at the boundary itself. No alarm sounds, no force suddenly increases. Locally, physics continues as usual. Globally, the structure of connection changes. This understanding replaces mystery with structure. It allows us to speak clearly about what an event horizon is, and just as importantly, what it is not. It is not destruction. It is not disappearance. It is not the end of reality. It is a limit on influence. And once that limit is understood, the concept becomes stable and calm, something that can be held without tension. As the ideas slow now, there is nothing more you need to follow or remember. The structure has already been laid out. Event horizons do not demand effort. They do not require vigilance. They exist whether we think about them or not, shaped by the same steady rules that govern everything else. Gravity curves, light travels, time moves forward. You can let your attention rest in that consistency. There is no need to imagine falling, crossing, or reaching anything. Just the knowledge that the universe is orderly, even at its limits, especially at its limits. As breathing softens and thoughts become quieter, the idea of a boundary can feel reassuring rather than unsettling. It tells us where things are stable, where rules hold, and stability is something the mind can rest within. The universe is not without limits, but its limits are calm. They are drawn by simple rules, applied patiently over time. An event horizon is one of those limits. Not a wall, not an ending, just a boundary in how futures connect. You don't need to hold the concept anymore. It can fade into the background like gravity itself, always present, never demanding attention. Let the steady motion of the universe continue without effort. Let thought loosen. Let rest arrive naturally. Everything flows. Sleep in that motion.